For more than 10 million years, an ancient interstellar wanderer lay preserved in the frigid depths of space, untouched by the warmth of any star, drifting in absolute silence to the cosmic void. Then, without warning, as it hurtled past our sun, Comet 3I Atlas erupted into life, a pristine world suddenly supercharged by an overwhelming shock of solar energy, now explosively ejecting vast clouds of chemicals and cosmic dust into space. Scientists are left wondering, will Earth soon encounter this matter carrying the very building blocks of life itself? But what force triggered this spectacular cosmic awakening? And how close are we to witnessing an event that could fundamentally reshape our understanding of life's origins throughout the universe? Comet 3I Atlas began its epic journey billions of years ago, most likely in the distant, frozen outskirts of a long-lost star system. Scientists estimate its age somewhere between 3 and 11 billion years, meaning it formed during an era when our Milky Way galaxy itself was still in its youth. For at least the last 10 million years, this remarkable object has wandered alone through the galaxy, never once passing close enough to any star to feel its warmth. This extraordinary period of isolation has been confirmed through precise analysis of star catalogs, which trace its trajectory far from any stellar encounter across the eons. During this immense span of time, 3I Atlas drifted to the cold, utterly dark reaches of interstellar space. In this realm of absolute isolation, the only energy reaching its frozen surface came from galactic cosmic rays, high-energy particles that bombard exposed materials relentlessly, even in the complete absence of sunlight. Over millions upon millions of years, these cosmic rays penetrated the upper layers of the comet, systematically breaking apart simple molecules and driving the slow, patient formation of increasingly complex chemistry. The result of this process is a surface crust enriched with ices, organic compounds, and radiation-altered materials, gradually thickening layer by layer as the object aged through the millennia. This crust functions as a chemical archive, meticulously preserving the products of cosmic ray processing alongside the raw ingredients gathered from ancient molecular clouds encountered during its journey. Deep beneath this altered surface, more pristine layers remain completely untouched, locked safely away from even the harshest radiation. By the time 3I Atlas finally entered our solar system, it carried with it billions of years of accumulated chemistry, an ancient record, dormant and patiently waiting for a new source of energy to awaken its hidden potential. As 3I Atlas approached our sun, the environmental conditions surrounding it transformed in a dramatic instant. Throughout its long existence in deep interstellar space, it has spent countless eons exposed to only the faintest trickle of cosmic rays. But as it neared perihelion, its closest approach to the sun, the solar energy it received skyrocketed to staggering levels. At its closest point to the sun, positioned just inside the orbit of Mars on October 29th, the comet's surface was suddenly blasted with approximately 735 watts per square meter. This represents an energy leap of more than 10 billion times the flux it had experienced, while drifting silently between the stars. For a celestial body that had been frozen solid for millions of years, this sudden exposure constituted an environmental shock unlike anything it had experienced since its distant formation in another star system. The sun's influence extended far beyond light alone. As 3I Atlas raced along its inbound trajectory toward the inner solar system, it encountered a relentless series of solar storms, powerful waves of charged particles and magnetic turbulence hurled outward by the sun's violently active surface. These storms injected intense bursts of energy into the comet's developing coma, violently stirring up the outer layers and driving chemical reactions that had lain dormant for ages beyond measure. The combined effect of intense sunlight and these energetic particles acted as a powerful catalyst, rapidly heating the ancient crust and triggering profound changes deep beneath the surface layers. This energy surge was far from a gradual warming process. The rate and scale of the heating completely overwhelmed the crust's ability to insulate the interior. Subsurface ices, previously locked away in stability for millions of years, began to destabilize catastrophically. The object's chemistry, preserved in an inert state for eons, was suddenly and violently set in motion. In this new, energetic solar environment, 3I Atlas was no longer merely a passive traveler drifting through space. It had become an active, dynamic participant in the solar system, primed and ready for the dramatic events that would soon unfold. Around early September, when 3I Atlas reached a distance of 2.53 astronomical units from the Sun, astronomers recorded an abrupt and sustained surge in brightness, nearly 2 full magnitudes brighter than any predictions had suggested. This was no fleeting outburst that would fade within hours or days. Instead, the entire object seemed to awaken from its ancient slumber, and the dramatically elevated brightness persisted for weeks, carrying through its closest approach to the Sun. Photometric tracking revealed that this brightness jump was not merely a localized event on one portion of the surface, but rather a global transformation affecting the entire comet. The dust output soared to unprecedented levels, with mass loss rates climbing dramatically from 0.3 kilograms per second up to an astounding 4.2 kilograms per second. Remarkable figures for any interstellar visitor, especially one of relatively modest size. The mechanics behind this extraordinary event point to a cryovolcanic, world-encompassing surge of activity. As the Sun's energy reached a critical threshold, heat began to penetrate through the porous crust, destabilizing vast reservoirs of ices buried beneath the surface. The comet's 16.16-hour rotation period played a crucial role in this process, distributing solar energy evenly across the entire surface and preventing any single hemisphere from either overheating or remaining frozen. This remarkably uniform heating allowed subsurface pockets of volatile material to warm up nearly in synchronization across the comet, building pressure simultaneously across much of the surface area. When that accumulated pressure finally broke through the weakening crust, the result was not merely a handful of isolated jets erupting from a few active regions. Instead, what occurred was a planet-wide release, gas and dust erupting explosively from countless locations across the entire nucleus. The brightness spike sustained itself well beyond the initial activation, confirming that 3I Atlas had undergone a complete transition from a dormant relic of interstellar space to an actively outgassing celestial body. The material thrown violently outward during this surge would go on to shape the complex jets and tails observed in the following months, setting the stage for the most puzzling and extraordinary features yet to be discovered. Jets of gas and dust now arc gracefully away from 3I Atlas, stretching outward as far as 50,000 kilometers from the nucleus, a distance greater than the circumference of Earth. These streams did not simply fan out at random like typical cometary missions. Instead, they form sharply defined, wavy filaments that twist and bend in unexpected patterns, hinting at powerful and unusual forces at work beneath the surface. While most comets predictably produce tails that point directly away from the Sun, driven by solar radiation pressure and the solar wind, 3I Atlas has defied conventional expectations in spectacular fashion. A sunward-facing jet, brighter and longer than any previously observed, has continued to grow even as the rest of the coma gradually fades. This striking anomaly has genuinely puzzled comet scientists, because solar radiation pressure and the solar wind should physically push material outward, away from the Sun, not back toward it. The answer to this mystery may lie in the object's highly unusual chemical composition. 3I Atlas is loaded with substantial quantities of nickel and iron, metallic elements that, when mixed with liquid water in the comet's interior, corrode and transform into magnetite, a mineral renowned for its strong magnetic properties. Magnetite can generate localized magnetic fields, and when combined with the plasma environment produced by the comet's vigorous outgassing, these fields can reach impressive strengths of 30 to 50 nanotesla under normal conditions, sometimes spiking dramatically to 300 nanotesla during intense solar storms. Such a magnetic field is strong enough to actively steer charged particles through space, shaping the trajectory of jets and even bending them sunward against the powerful flow of the solar wind, a phenomenon rarely observed in our solar system. The result is an intricate, complex dance between plasma, dust particles, and magnetic fields that sculpts the comet's jets into structures unlike those seen in typical solar system comets. This self-generated magnetic cocoon does not merely create a visual spectacle for observers. It may also serve a more profound purpose, helping preserve the fragile organic molecules embedded within the comet's material, shielding them from destructive radiation as they travel through the harsh environment of space. The OSIRIS-RX mission's historic return of pristine samples from asteroid Bennu has fundamentally transformed the search for life's building blocks in space, moving the discussion from abstract theory to concrete laboratory fact. Scientists discovered an impressive suite of organic molecules within Bennu's dark, carbon-rich regolith, including glucose, ribose, and a diverse range of nucleotides that form the structural backbone of DNA and RNA, the very molecules that encode life as we know it. An astonishing 33 different amino acids were cataloged from the samples, including 14 that are absolutely essential to human biology and metabolism. Water was also present in significant quantities, locked within mineral structures and existing in briny mixtures, confirming that liquid phases once existed on this small world, despite its current frozen state. Bennu is classified as a B-type asteroid, meaning it has been more significantly altered by heat over its lifetime and is theoretically less likely to retain fragile organic compounds than the even more primitive D-type asteroids and trans-Neptunian objects found in the outer solar system. Yet despite this processing, its chemistry remains remarkably rich and diverse. The implications are straightforward and profound. If Bennu, a thermally processed remnant from our own solar system's early history, carries such extensive and diverse inventory of prebiotic molecules, then 3I Atlas, whose spectral fingerprint closely matches the more volatile-rich, organic-laden CR carbonaceous chondrites, should logically be even more enriched with these crucial compounds. Detailed spectroscopic analysis of 3I Atlas reveals a carbon dioxide to water ratio near 8:1, far above that of typical solar system comets, and a carbon monoxide to water ratio of 1.65:1, both clear signatures of active, ongoing chemistry. When combined with the groundbreaking results from Bennu, the accumulated evidence substantially raises the odds that 3I Atlas is not merely a carrier of water, ice, and simple dust, but rather a vessel loaded with the raw chemical ingredients necessary for life itself. The question now shifts from what 3I Atlas carries within its ancient structure to what it might actually deliver to our world. For decades, scientists have vigorously debated whether objects like this could successfully transfer the chemistry of life between distant star systems. The mounting evidence from 3I Atlas, its substantial load of water, complex organics, and sophisticated molecules, brings that once theoretical debate out of the realm of speculation and into the domain of direct observation and measurement. The object's estimated size, somewhere between 0.3 and 5.6 kilometers across, means it is large enough to effectively shield fragile organic compounds from destructive cosmic radiation over billions of years of interstellar travel, yet small enough to shed substantial amount of material as it passes close to an energetic star like our Sun. The timeline for this cosmic delivery is now firmly established. First discovered on July 1st, 2025, Comet 3I Atlas reached its closest approach to the Sun on October 29th of the same year. It will swing past Earth on December 19th, 2025, coming within 1.8 astronomical units, relatively close by cosmic standards, though still far beyond the Moon's orbit. But the most scientifically intriguing date lies just ahead in our immediate future. In March and April 2026, Earth's orbital path will carry us directly through the region of space where 3I Atlas released its perihelion debris, the material violently ejected during its closest approach to the Sun. For the scientific community worldwide, this represents far more than an astronomical curiosity or a minor event to catalog. This is a testable, measurable event with profound implications. As Earth moves through the dust lanes and organic-rich material left behind by this interstellar traveler, researchers will be watching intently for telltale signs. Microscopic particles captured in the upper atmosphere, new and exotic compounds drifting down from the sky, perhaps even subtle but detectable changes in the chemical composition of rain or snow in the months following our passage through the debris field. The genuine possibility that our planet could directly sample material forged in orbit around another star, delivered to us by a visitor like 3I Atlas, transforms what was once an abstract, philosophical idea into a near-term scientific experiment with measurable outcomes. The next chapter in the epic story of life's cosmic journey may be written not in some distant future, but in the months immediately ahead of us. Right now, at this very moment, as Earth prepares to cross through the debris trail of 3I Atlas, we stand poised at a unique moment in human history, ready to witness interstellar organic molecules mingling directly with our own atmosphere for the first time in recorded history. The evidence continues to mount that the ingredients for life routinely travel between stars aboard ancient wanderers like this one, reminding us with humbling clarity that the origins of life are not fixed to any single world or star system, and that the story of life itself may be far more cosmic, far more interconnected, and far more ancient than we ever imagined possible. As December 2025 approached, scientific institutions across the globe mobilized with unprecedented coordination. NASA's WB-57F high-altitude research aircraft stood ready at their bases, equipped with specialized collectors designed to capture particles at 60,000 feet, well above commercial aviation, but squarely within the zone where 3I Atlas's microscopic debris would first interact with Earth's atmosphere. The European Space Agency positioned their atmospheric monitoring satellites into optimal orbits, their sensors calibrated to detect even the faintest chemical signatures. In laboratories from Tokyo to Toronto, mass spectrometers hummed to life, prepared to analyze atmospheric samples with extraordinary precision. Scientists established a global network of collection stations, from research vessels in the Pacific Ocean to remote Antarctic outposts where pristine snow could capture falling particles untainted by industrial contamination. Ground-based telescopes tracked the comet's fading tail, measuring its trajectory with exacting detail, while space-based observatories monitored the expanding debris field. The scientific community understood the stakes. If 3I Atlas truly carried complex organic molecules from another stellar system, detecting them in Earth's atmosphere would mark a watershed moment. Proof that life's ingredients weren't confined to our solar system's primordial soup, but instead traveled the galaxy on frozen arcs, seeding worlds across vast interstellar distances. On December 19th, 2025, as predicted with mathematical precision, 3I Atlas swept past Earth at a distance of 1.8 astronomical units, approximately 270 million kilometers. Though far beyond the Moon's orbit, this was close enough for detailed observation of the comet's ongoing transformation. Amateur astronomers reported seeing the comet as a ghostly smudge through their telescopes, its sunward jet still defiantly pointing toward our star, like a cosmic beacon. But professional observatories captured something far more intriguing. High-resolution spectroscopy revealed that the comet's chemical signature was changing in real time. The ratio of complex organic molecules to simple water vapor was increasing, suggesting that deeper, more pristine layers were now being exposed as the outer crust continued to sublimate away. The most sophisticated analysis detected molecular structures that matched none of the organic compounds typically found in solar system comets. Signatures that could only have originated in the chemistry of another star system. Dr. Sarah Chun, leading the International Observation Campaign from the European Southern Observatory, made a statement that would echo through scientific journals for months. We are not just looking at ice and dust. We are watching a chemical library from another stellar neighborhood revealing itself, page by page. As Earth continued its orbital dance, the clock ticked toward the critical encounter, the moment when our planet would cross directly through the debris trail left in 3I Atlas's wake. The first week of March 2026 arrived with a mixture of anticipation and careful scientific skepticism. Initial atmospheric samples showed nothing unusual. The ordinary mix of terrestrial particles, volcanic ash, and standard cosmic dust. Then, on March 9th, everything changed. High-altitude collectors aboard NASA's research aircraft detected unusual particles during a routine sampling run over the mid-Pacific. These weren't the typical micrometeorites that constantly rain down on Earth. Under electron microscopy, they revealed a distinctive structure, porous, fluffy aggregates unlike anything in the terrestrial particle catalog. More significantly, their chemical composition was extraordinary. Mass spectrometry revealed ratios of carbon isotopes that fell outside Earth's normal range, suggesting an origin beyond our solar system. Within these particles, scientists found complex polycyclic aromatic hydrocarbons, amino acids with unusual chirality, and most remarkably, what appear to be fragments of nucleobases, the fundamental building blocks of genetic material, but with molecular configurations never before observed in terrestrial or solar system samples. By March 15th, detection stations across the Northern Hemisphere were reporting similar findings. The particles weren't arriving in a single burst, but in waves, reflecting the complex structure of the comet's debris trail. Each sample revealed layers of information. Some particles showed heavy radiation damage from millions of years in interstellar space, while others appeared remarkably pristine, as if they'd been shielded deep within the comet's nucleus until the solar heating released them. On March 22nd, a team of biochemists at MIT made a discovery that would dominate headlines worldwide. Among the collected particles, they identified complete amino acid chains, not just individual amino acids, but linked sequences of up to 7 units. In the context of terrestrial biology, such chains would be called peptides, the precursors to proteins. But these weren't terrestrial. The amino acids were predominantly right-handed, opposite to the left-handed preference of Earth life. More stunning still, several of the amino acids didn't exist in Earth's biological repertoire at all. They were exotic variants, structurally similar to terrestrial amino acids, but with subtle differences that suggested formation under different chemical conditions, possibly around a star with a different spectral type than our Sun. The implications sent shockwaves through the scientific community. These weren't just the simple building blocks that could form randomly in space. These were complex, pre-assembled molecular structures that suggested organized chemistry. Not life itself, but perhaps the kind of sophisticated chemical evolution that could precede life emergence. Dr. James Okonkwo, an astrobiologist at Cambridge, captured the moment's significance. We're looking at chemistry that evolved over billions of years in an environment we've never seen. These molecules may represent a parallel path of chemical evolution, one that never progressed to life in their home system, but carried the potential across the galaxy. And now that potential has arrived here. As April arrived and Earth continued through the densest part of the debris trail, the discoveries accelerated. Research teams in Japan identified particles containing magnetite crystals with embedded organic inclusions, exactly the kind of structures that 3I Atlas's magnetic environment would create. These crystals appear to have protected their organic cargo from radiation damage, creating pristine time capsules of ancient interstellar chemistry. More intriguing still, chemical analysis revealed that some particles contain water, not as ice, but as water molecules trapped within the crystalline structure of minerals. Isotopic analysis of this water showed deuterium ratios different from Earth's oceans, confirming its extraterrestrial and likely interstellar origin. Then came the finding that would transform the entire investigation. On April 7th, a collector station in northern Canada recovered particles that contained complex ring structures of carbon, nitrogen, and phosphorus atoms arranged in patterns that closely resembled, but weren't quite identical to, the structure of RNA nucleotides. These weren't the nucleotides themselves, but something tantalizingly close. Molecular structures that, with just a few additional chemical steps, could transform into the information-carrying molecules of genetics. The scientific community faced an unprecedented question. Had 3I Atlas delivered not just the ingredients for life, but molecules that were just one or two chemical reactions away from becoming the machinery of life itself? By mid-April, an unexpected phenomenon emerged that nobody had predicted. Meteorological stations began detecting subtle but measurable changes in upper atmospheric chemistry. The influx of organic particles was catalyzing reactions in the ionosphere, creating transient layers of complex molecules at altitudes between 80 and 100 kilometers. These layers were ephemeral, lasting only hours before solar radiation broke them down. But during their brief existence, they represented something remarkable. Earth's atmosphere was actively processing interstellar organic material, potentially creating new molecular combinations that had never existed in either location, hybrid chemistry from two stellar systems. Auroral researchers reported unusual optical emissions during aurora events over this period. Faint green and purple glows that spectroscopy revealed came from the fluorescence of exotic organic compounds interacting with Earth's magnetic field. The sky itself was glowing with the light of molecules from another star. The most extraordinary discovery came in late April, during a series of spring storms over the Pacific Northwest. Atmospheric scientists had predicted that the organic particles, once they descended into the lower atmosphere, would be incorporated into precipitation. What they didn't predict was how detectable this would be. Dr. Rachel Iverson, a geochemist at the University of Washington, led a team collecting rainwater samples during these storms. Analysis revealed that the rain contained measurable concentrations of interstellar organic compounds, concentrations far too high to be background contamination. The organic molecules were falling from the sky in quantities sufficient to be chemically significant. Local news stations ran stories about alien rain, though scientists were careful to clarify that no life or living organisms were involved. Yet the implications were staggering. Interstellar organic material was literally falling on Earth's surface, on forests, oceans, agricultural fields, and urban areas. It was mingling with terrestrial ecosystems, being absorbed by soil, taken up by plant roots, potentially entering the global carbon cycle. Soil scientists began collecting samples from areas exposed to these rains, planning long-term studies to track whether any of these exotic molecules would persist in terrestrial environments or be quickly broken down by Earth's aggressive biochemistry. By May 2026, as Earth emerged from the densest part of the debris field, the scientific papers began flooding journals. Over 200 research groups across 40 countries had participated in the collection and analysis effort, generating the largest coordinated astrobiological data set in history. The findings were compiled, peer-reviewed, and released in a special issue of Nature that will become one of the most cited scientific publications of the decade. The conclusions were carefully worded but revolutionary in their implications. Interstellar organic delivery is real. Complex organic molecules can survive journeys of millions of years between star systems, protected within cometary nuclei. Pre-biological chemistry is widespread. The molecular complexity found in 3I Atlas's debris suggests that the chemical evolution leading toward life is not unique to Earth, but may be a common feature of galactic chemistry. Panspermia remains possible, while no living organisms were detected. The discovery of near biological molecules raises the probability that actual life, in dormant forms, could theoretically survive interstellar transfer. Earth has been enriched. For at least several months in 2026, Earth's environment contained and processed organic material from another stellar system, making our planet, however briefly, a hybrid of two cosmic neighborhoods. As the year progressed and the media excitement settled into long-term research programs, one profound question continued to resonate through scientific discussions and public consciousness alike. What if 3I Atlas wasn't unique? Statistical models suggested that dozens of interstellar objects might pass through the inner solar system each decade, most too faint or moving too fast to detect. If just 1 in 10 carried organic material similar to 3I Atlas, then Earth might be experiencing interstellar chemical delivery events regularly, invisible rain from the stars that has been falling for billions of years. Some researchers speculated whether Earth's own origin of life, some 3.8 billion years ago, might have been influenced or catalyzed by similar deliveries. Perhaps the chemical soup from which Earth's first microbes emerged was never purely terrestrial, but always a cosmic mixture, a blending of local chemistry with molecular complexity delivered from the stars. Others look forward, considering what this means for life elsewhere. If organic complexity travels between stars, then no planetary system evolves in isolation. The galaxy itself becomes a vast interconnected web of chemical exchange, with comets serving as messengers carrying billions of years of evolved chemistry from one stellar nursery to another. As December 2026 approached, 1 year after 3I Atlas's close approach, the comet itself had long since departed, racing back out toward interstellar space on a trajectory that would carry it away from the sun for millions of years. Its magnetic jets had faded. Its outgassing had ceased as it retreated beyond the orbit of Jupiter into the cold, where it would return to dormancy. But its legacy remained. Samples collected during the crossing were distributed to hundreds of laboratories worldwide, each seeking to unlock different aspects of the comet's chemical story. Graduate students began dissertations that would take years to complete. New instruments were designed specifically to detect and analyze interstellar organic material. Funding agencies, convinced by the spectacular results, allocated substantial resources for the next generation of interstellar object detection and sample return missions. Perhaps most significantly, the detection of 3I Atlas changed humanity's perspective on its place in the cosmos. We were not isolated on a lonely planet orbiting an ordinary star. We were part of a galactic ecosystem, connected by wandering messengers like 3I Atlas that carried chemistry and perhaps the seeds of life itself between the stars. The ancient interstellar traveler had awakened not just from its own dormancy, but had awakened in humanity a new understanding that the story of life on Earth is inseparable from the story of the galaxy itself. We are and always have been children of the stars, not metaphorically, but chemically, molecularly, tangibly real. And somewhere in the darkness between stars, countless other frozen wanderers continue their journeys, carry within them the accumulated wisdom of billions of years of cosmic chemistry, waiting for the warmth of a star to awaken their ancient cargo and share it with whatever worlds they might encounter. The crossing of 3I Atlas was not an ending, but a beginning. The first chapter in humanity's direct engagement with the chemistry of distant stars, and perhaps in time with the revelation that life itself is not a planetary phenomenon, but a galactic imperative, written in molecules that travel the cosmos on frozen arcs, patiently waiting for the right world to receive their ancient message.